Hello, am I audible? Okay, so are there any questions, doubts? Yes? Okay, so if there are no questions, let me start. So last class we discussed basically the plane stress, plane strain element, basically a three-noded triangular element. And today I am going to talk about four-noded rectangular element and then actually a general quadrilateral. And to satisfy the compatibility, we have to do the formulation in natural coordinate space. So that is what I will discuss today. So first, let me discuss four-noded rectangular element. For the same, maybe for the heat conduction problem, of course this in a similar manner you can extend it for the plane stress plane strain problem. Hello, is my screen visible? Okay. So I am going to discuss, as I said, four noded rectangular element in physical coordinate space. That means we do the interpolation in xy in physical coordinate space. And we will take the example of a 2D heat conduction problem. And then of course the same thing can be extended for uh, stress strain problem. So now what I will do is, of course, when we formulated the triangular element, we did the formulation in terms of global coordinates x and y. But here I am going to use the local coordinates so that the shape functions are easy to write. So this is global coordinate system, and then we have this rectangle, not a arbitrary quadrilateral but a rectangle. So the rectangle is the local coordinate is capital X and capital Y. This is node 1, this is node 2, this is node 3, and this is node 4. And then the coordinates, local coordinates would be, the coordinates of this point would be 0 0, and the coordinates of this node are say a comma 0, a comma b, and 0 comma b. So these are the coordinates. So that means no, this length is a and this is b. And at each location we have temperature as a degree of freedom because we are talking of heat conduction problem. So here T1e, and then we have T2e, T3e, and T4e. So these are the temperature degrees of freedom. So as usual, the first step is to assume an approximate solution. So if you look at the approximate solution, so now since of course we know that temperature is a primary variable, so it has to be a degree of freedom at the nodes, and that is what we have. and then there we have total four elemental degrees of freedom. So whatever approximate solution we assume should have four known constants. So therefore we write t, and we are going to assume this interpolation in terms of local coordinates capital X and capital Y. So we will assume t equal to a0 plus a1x plus a2y plus a3xy. So this will be the approximate solution, and then now we write the constants a0, a1, a2, a3 in terms of values of t at nodes 1, 2, 3, and 4. So that is, we can say t1e would be equal to value of t at x and y equal to 0. So you simply get a0. So you can say a0 is nothing but t1e. And then if you look at T2E, which is the value of temperature at node 2, where the x coordinate is small a and y coordinate is 0. So you get A0, A0 is already T1 into E, and plus we will have A1 into A, and the y coordinate is 0. So these are the only terms you get. So therefore from this equation you can straight away say that A1 is equal to T2E minus T1E upon small a. And then if you look at node 4, so t4e would be equal to, now for this node the x coordinate is 0, y coordinate is b. So we get a0, a0 is t1 into e, plus x is 0, so this term will go to 0, and then we will have plus a2 into y, which is b. So therefore from this equation you can say the constant a2 would be equal to t4e minus t1e upon b. And then if you look at the node 3, so t3e, at node 3 x and y coordinates are a and b. So we will have a0, which is t1e plus a1 into x, and a1 we have seen here, it is t2 minus t1e divided by a into a, the x coordinate is a, plus a2 into y, and a2 is t4e minus t1e upon b into y coordinate is b, and plus we will have a3, and x coordinate is a, y coordinate is b. So from this equation you can see, you can solve for actually no a3, the unknown constant a3. So a3 would be, you will be find that it will be t1 minus t2e plus t3e minus t4e divided by a into e. So this is what the constants a0, a1, a2, a3 are going to be there. And now if we let us call this as equation 2, and the whatever constants we have got is we have already there. So now if we substituting a0, a1, a2 and a3 in equation 1, what do we get? We get actually the interpolation for t. So you will get that when you collect the coefficients of t1e, t2e, t3 and t4e, so you get the shape functions. So essentially this would be equal to n1, n2, n3 and n4. Now there would be four shape functions because there are four nodes, and at each node we have 1 degree of freedom, that is value of temperature. So t1e, t2e, t3e and t4e. So now here, of course, now you write this as usual, t equal to interpolation matrix H into vector of elemental degrees of freedom d. So this is your H, and this is your basically vector de. And now here, if you see the shape functions, so you will find that n1 would be equal to actually 1 minus x upon a into 1 minus y upon b, and 2 you will find. So I will also explain you how to directly write these shape functions. So n2 would be x upon a into 1 minus y upon b, n3 in a shape function 3 would be x upon a into y upon b, and shape function n4 would be y upon b into 1 minus x upon a. So you will have actually some kind of a direct interpretation of these shape functions. So if you look at the element, this is the element, the local coordinate is x and this is local coordinate y, and this dimension is a and this is b, and these are the nodes 1, 2, 3 and 4. So n1 is the shape function corresponding to node 1. So it has to be unity at node 1 and 0 at node 2, 3 and 4. So you will find that actually if you put node 1 means x and y are 0. So if you put x and y equal to 0, you get n1 equal to unity. And node 2 means x is equal to a, y equal to 0. If you put that, it comes out as 0. Similarly at node 3, x and y are a and b, so it is 0. And at node 4, x is 0, y is b, so there also it is 0. So to write this shape function, what you can do is, suppose if you want to write the shape function corresponding to node 1, of course it comes from no this that is substituting the a0, a1, a2, a3 in equation 1 and then collecting the coefficients of t1, t2, t3, t4, but it can be written directly. So when you are writing the shape function corresponding to node 1, you take the equations of no the line leaving the no covering the other nodes and leaving the node 1. So the other nodes are 2, 3 and 4. So if we want to cover the node 2, 3 and 4 using minimum number of lines, so we'll take one line, no this line whose equation is basically x is equal to a. The equation of this line is x is equal to a. So this equation can also be written 1 minus x upon a equal to 0. So you take the, and similarly the for this line y equal to b, so this can also be written as 1 minus y upon b equal to 0. So you take the product of these two equations of line, that is 1 minus x upon a, 1 minus y upon b, and that gives you the shape function n1. And then to write n2, you take the equation of this line and equation of this line. So equation of this line is already 1 minus y b 1 minus y by b equal to 0, and the equation of this line is x equal to 0. I can say x upon a equal to 0. So you multiply the equation of this line, which is x upon a equal to 0, and the equation of this line, which is 1 minus y upon b equal to 0. So that gives you the shape function n2. For n3, because this is the node 3, so you take the equations of the lines which are covering the other nodes. So that is this line and this line. The equation of this line would be y upon b equal to 0. So the product of these two equations of lines, so x upon a into y upon b would be n3. And then to write n4, you take now the lines covering node 1, 2 and 2, 3. So for this, the equation of line is y upon b, and the equation of this line is 1 minus x upon a. So you get this shape function. So you can also directly write these shape functions. So what I wanted to tell you is that you can directly write the shape function. Of course, the element is a rectangle. So for that, we are able to easily write these shape functions. So once, yeah, so other aspects, if you look at, no, there are basically the development of the element level governing equation, and you will now, I think by now you would notice that this is a standard procedure actually, the development of element level governing equation. So what we can do is, now we have to write the temperature gradients, because in the integral functional we had seen for the 2D heat conduction problem there is a temperature gradient del T by del X. So now here the derivatives are with respect to capital X and capital Y. So let me write that. So derivative with respect to capital X and derivative with respect to capital Y. So these will be as usual. No, we have been writing that. So we know t equal to n1 t1 plus n2 t2 plus n3 t3 plus n4 t4. n1 n2 n3 n4 are the functions of x and y. So we take their derivatives. So we will get del n1 by del x, del n2 by del x, del n3 by del x, and del n4 by del x. And similarly del n1 by del y, del n2 by del y, del n3 by del y, and del n4 by del y. So into the vector of elemental degrees of freedom. So that is T1E, T2E, T3E, and T4E. So this is as usual in our standard notation. We call this as the gradient matrix B, and this as the vector of elemental degrees of freedom. So this is B, this is D. And now we know is the same. You have the same integral functional for 2D heat conduction problem. So we basically substitute this approximation in that and get the element level governing equation. So let me. I think I assume now that no, given the differential equation or the big form or the integral functional, you should be able to, for any problem you should be able to develop the integral functional, and substituting the approximation in that you should be able to develop the element level governing equations. So I'm directly writing that. So the element level governing equation for this problem is going to be, the form of the element level governing equation is same. We are taking the, considering the steady state heat conduction problem. So this is equal to F external for the element and plus F internal for the element. So yes, once you have this, of course we have to define the basically the matrices. So where Ke, the element level conductance matrix. Now the integration limits we know because the element is a rectangle. So my, let me put that. So integration 0 to A, integration 0 to B in the local coordinate system, and then we have K into H. H is the thickness, and B transpose into B into dx dy. The limit of x is 0 to a, limit of y is 0 to b. So of course you have to carry out, no, you have, because you know the shape function, you can differentiate that, get the derivatives of shape functions with respect to x and y, put them here, and then do the integration. You will find in this case that b is not going to be constant. So actually you'll have to put the derivatives, multiply, carry out the integration, then you get the conductance matrix Ke. So that you should actually do as an homework problem. So now f external will be of course again integration 0 to a, integration 0 to b, and then we had h into h transpose into qg heat conduction into dx dy. And of course the internal load would still remain in terms of the boundary integral. So in the integral along the boundary of the element, so that is h transpose into qn into h into ds. So this is the element level governing equation. And as a homework problem, so the homework problem is derive the final expression. So that is after integration, derive the final expressions for Ke and F external E, taking H equal to constant within the element. So this is straightforward. Only thing you have to, of course, know the shape functions are there. You have to differentiate, get the B matrix, multiply, and then integrate. The integrations are also going to be straightforward. So you will get the for Ke. Of course, the Ke will be now 4 by 4 because B is 1 by 4. B transpose is going to be 4 by 1. So earlier for the triangular element it was a 3 by 3 matrix. Now it would be a 4 by 4 matrix, and this would be a 4 by 1 vector. 4 by 1, this is also going to be 4 by 1. So now usually see if the domain is rectangular, then you can discretize mesh that using rectangular elements. But that is most of the situations we will deal with for that. Actually the domain, the heat conduction domain where we want to solve the problem, temperature distribution, the domain may not be rectangular, so it may be irregular. For the irregular geometry, then you cannot use the rectangular element. You have to use arbitrary quadrilateral, at least arbitrary quadrilateral. So, let me. The problem with the arbitrary quadrilateral is that it will not satisfy the compatibility condition. So if I take arbitrary quadrilateral, not a rectangular but arbitrary quadrilateral. element formulated, and still we are trying to assume the approximate solution in the physical coordinate space, that is xy coordinate space. So I'm saying formulated in physical coordinate space. Physical When I say this, that is the approximate solution is assumed in terms of physical coordinate space. So physical coordinate space, that is in terms of x and y. So it does not actually satisfy inter-element compatibility. Inter-element compatibility. So how? So let's argue out. So the element we are talking about is, since this is arbitrary quadrilateral, I am writing now going to write the approximate solution in terms of the global coordinates x and y. Arbitrary quadrilateral means edges are not parallel to x and y. So this is, say, one is, this another is, this is it, another is. So this is the element, and these are the nodes. The coordinates are going to be nodes are 1 2 and 1 2 3 4, and of course the degrees of freedom would be value of temperature here, T1e, T2e, T3e, and T4e. The coordinates would be x1 and y1, x2 and y2, x3 and y3, x and y coordinates which are known. The coordinates of this would be x4 and y4. So for this, if you look at the approximate solution again, the temperature values are there as degrees of freedom at the nodes, which are primary variables. There are four degrees of freedom per element for the element as a whole. So we can take the approximate solution which has four terms, and of course that will satisfy the differentiability requirement within the element. So we can take this as a0 plus a1x plus a2y plus a3xy, and of course the steps to develop the shape function and the element level governing equations would be that we first express a0 a1 a2 a3 in terms of t1e t2e t3 t4e, and then get the shape functions and then put that in the integral functional or the weak form and get the element level governing equation. So what I am going to discuss is only the compatibility condition. So now the compatibility condition is, let us say that we have a domain, and uh, this is the domain, and let us say we discretize this using two elements. These are arbitrary quadrilaterals. So this is element 1, this is element 2, and these are the nodes. I'm just taking an example to demonstrate the whether how the inter-element compatibility is not satisfied. So let us say this common edge is AB. AB is common edge, as you see over here. So the common equation of common edge AB, its equation is, it is a straight line. So either you can express y in terms of x or x in terms of y. So that would depend on the coordinates of a and b. So right now I'm just putting a general way. So you can write the equation of line AB as capital A0 plus A1 into x. So this is the equation of line AB. Now if I want to look at the variation of t, variation of t along AB. So let me call that as TAB. So TAB now along AB, y equal to A0 plus A1x. X and y are not independent along AB, but y can be expressed in terms of x or x can be expressed in terms of AB, because either y can be expressed in terms of x or x can be expressed in terms of y along line AB. So the two coordinates are not independent, so we'll have to put that. So now if you look at T will be along line AB would be A0 plus you have a1 into x, and then we have a2 into y, and y is nothing but capital A0 plus a1x along line AB, and then plus we have a3 into x into y, and y is a0 plus a1 into x. So you will find in this that when you look at the constant term, so this a0 plus a2 into a0, this is a constant term. So you can write this equation as a0 plus a2 into a naught. That is one equation. Now if you look at the terms linear in x, so one term is this a1 you have, and then you have this a2 plus a1, and the other term you have is this a3 into a naught. So this whole thing into x, and then you will find that we have no quadratic term, and which is a3 into a1 into x square. So you can now write this equation as something like basically b0 plus so it's a quadratic as you see, so you can write this something like b0 plus b1x plus b2x square. Now what does this equation tell us? That the temperature variation along AB is a quadratic function of x. Along line AB, where line AB is arbitrary line. If it was parallel to x or y, then the equation of the line would have been either x is equal to constant or y equal to constant, and in that case we will get the temperature variation linear along AB, and then it would be compatible. That means it will satisfy the continuity of temperature along line AB. Of course, at A and B both the elements will have same temperature, because that we are going to enforce in the assembly. But along line AB now, because at A both elements have got the same temperature degree of freedom, let us say TA is the temperature degree of freedom at node A, and TA will be same for element 1 as element 2 at this particular node. And let us say at B the degree of freedom is TB. So TB is the same value of temperature at this node of the element 1 and this node of the element 2. So it is same. So the two degrees of freedom are common. But now if it was a linear polynomial, if it was TAB was simply B0 plus B1x, so then this B0 and B1 we could have got in terms of TA and TB, and then we would have got the same unique variation of temperature along AB from element 1 and 2. So therefore the compatibility would have been satisfied. But in this case it is quadratic, so using two values Ta and Tb, we cannot get the constants b0, b1, b2 uniquely. So therefore no, when you look at, you will get a temperature distribution. Let's say from element 1 it would be like this, and maybe element 2 may give you a temperature distribution like this. So this is the temperature distribution from element 1 along line AB, and this is the temperature distribution from element 2 along line AB. So the two data elements are not giving the same temperature distribution along line AB, and therefore this element is not compatible. So it does not satisfy inter-element compatibility condition. Whereas if it was a rectangular element, as I said earlier, so this equation simply would have been y equal to constant, and if you would have put y equal to constant here, you would have got tab as linear function of x. And then if it is linear and at a and b we have same values of temperature in both the elements, so in between it is going to be a unique variation. So both elements 1 and 2 would give you the same temperature variation along AB. So basically we will get the we will satisfy the compatibility condition. So now what do we do? So next question is, we need arbitrary
Okay, sir.
coordinate. Yeah.
Sir, can you please repeat the last part again?
Last part, no, what I said for
After
the
this quadratic.
quadratic element, no, the same element you are talking about, this one or the rectangular element?
So the same
Last
one. So the same concept only. After we have derived this quadratic equation, after that you told some concept. Can you please repeat that?
Yeah, so okay, so what I said is that no, now when you look at these two nodes A and B, so at these two nodes we have the temperature Ta and Tb, and this Ta is same basically common to element 1 as well as element 2. Similarly Tb at node B is common to element 1 and 2. So these are the two temperature values which are same no, in element 1 and element 2. So when we look at this quadratic variation of temperature along AB, so there are three constants B0, B1 and B2. So now these three constants cannot be expressed in terms of no, the two temperature values Ta and Tb, because no, there are two values and three constants, so they cannot be expressed in terms of two constants. So then what will happen is, because no, these constants will depend on, say for element 1, these constants will also depend on the temperature values at this node and this node. For element 2, these constants will be depending on the no element no this node and this node also. So what I said is, maybe element 1 would give a temperature distribution like this, element 2 would give a temperature distribution like this. So there is a difference in the temperature distribution predicted along line AB. So that means the temperature distribution predicted from element 1 and element 2 is not same along line AB for this arbitrary quadrilateral element, and therefore it does not satisfy the inter-element compatibility. That is what I said. So then I also mentioned that if the element is a rectangle, so that means if the edges are parallel to x or y, so this equation would have been simply y equal to a constant value. And if you would have substituted that y equal to constant in this expression, you would have got TAB equal to B naught plus B1x, which involves two constants. So the two constants can be determined in terms of the temperature Ta and Tb, and that would be unique for both the element 1 and 2. So it will give you the same temperature distribution along AB, whether be predict from element 1 or be predicted from element 2. So therefore it would satisfy the inter-element compatibility. So the nutshell I wanted to say over here is that arbitrary quadrilateral with interpolation of unknown variables in physical xy coordinate space does not satisfy inter-element compatibility. So that's an incompatible element. So therefore we have the concept of, is that clear now? Hello, is it clear or no?
Yes, sir.
So basically
Sir,
there are
when you are talking about the AB being parallel to one of the edge, sir,
yeah.
then we are talking in local coordinate system.
Yeah, it can be actually in global also, but for the purpose of writing the shape function, we use the essentially local coordinate system. But when you have a rectangular element, even if it is formulated in the global coordinate system, then also it is same. Only requirement is that the edges should be parallel to x and y. So even if this is the situation, you have t equal to a0 plus, in this case, derivation of the shape function would be a bit more involved, because the coordinates would be here x1 and y1, which are not 0, here x2 and the y2. Of course, you will have y1 and y2 same for the rectangular element, and this would be x3 and y3, and you would see x3 would be same as x2, and this would be x4 and y4, and you will see y4 would be same as y3 and x4 would be same as x1 for a rectangular element. So in that case you will have the approximation as t equal to a0 plus a1x plus a2y plus a3. You can do in the local coordinate system or the global, it doesn't matter, it give you the same thing. And now when we have assembly of these elements, so let us say if I just take two elements, and this is the common edge, this is element 1, this is element 2, this is line AB. So the equation of line AB, if you look at, is simply you have you can say in this case x is equal to constant. So if I write x is equal to constant, say some constant value xc, which is constant. So now if you look at t will be a0 plus a1 into xc plus a2 into y plus a3 into xc into y. So you would see no these two terms are now constant, a0 plus a1 into xc, these are constant terms, and then you have a2 plus a3 xc into y. Now y is only variable, so you can say this is some kind of b0 plus this t along ab, so b0 plus b1x. So this would be linear in sorry, y, not x, y, b1y. So now these are two constants, and when we assemble the equation, we say that this node of element 1 and this node of element 2 have the same temperature, let us say Ta. And similarly for this node, we say that no, this node of belonging to element 1 and element 2 have same temperature, so let us say Tb. So now I can find out these constants b0 and b1 in terms of ti and tb, and that would be unique for both the element. So let us say we would get some unique variation along AB. Temperature distribution is going to be unique. So when I look at the temperature distribution, let us say from A to B, the temperature distribution comes like this. So this value is Ta over here, and this value is Tb over here. But this would be same from both the elements. This will be from element 1 as well as element 2. So both the elements in that case will give you the same temperature distribution along AB, and therefore it would be a compatible element. So you can either argue out in terms of global coordinate system, or you can argue out in terms of local coordinate system. For rectangular element, the end conclusion would be that it would be a compatible element. That means it would give the continuous distribution of temperature along a common edge. So that's the difference actually between one dimensional element. There we only required that if we have primary variable as degrees of freedom at the end nodes, we can satisfy the compatibility directly. But here in 2D and 3D elements, you will find that to satisfy the compatibility, it is not just enough to have primary variables as degrees of freedom at the nodes, but we have to make sure that along common edges, the variation of the primary variables is actually continuous. Then only we would be able to satisfy the compatibility condition. So now, of course, we cannot always model problems, idealize, solve problems using rectangular elements, but we have to use arbitrary quadrilaterals. So for that, then what we have is something known as the formulation in natural coordinate space. So if we have formulation in natural coordinate space, so then the element can be a arbitrary quadrilateral in physical coordinate space, but a square in the natural coordinate space. The interpolation is done in terms of natural coordinates, so it satisfies the inter-element compatibility condition. So next is the formulation in natural coordinate space. These natural coordinates I am going to denote by xi and eta. So basically in this what we are saying, when I am saying the formulation is in natural coordinate space, so what we want to have, we want to have element in R is arbitrary quadrilateral in physical coordinate space. Physical coordinate space, and we square in natural coordinate space. Natural coordinate space. Now, so before that, we should know, of course, what is natural coordinate. So essentially, the natural coordinates, as I said, zeta, eta, they vary from -1 to +1. So the coordinates which vary from -1 to +1 are referred to as natural coordinates. So natural coordinates. And now I am going to denote, as I said, xi and eta. This is xi, and the second one is eta. So they vary from -1 to +1. So now if you look at the element, so now we are going to have kind of a mapping. So there's another concept, mapping, over here. So the mapping means, suppose if I take the element in the physical coordinate space, so this is x and y, and then we have the element arbitrary quadrilateral, as you see over here, and these are the nodes 1, 2, 3, and 4, and let us say P is the any point having coordinates x and y, and the coordinates of nodes are x1 and y1, x2 and y2. These are the x and y coordinates would be known actually, and the coordinates of this would be x4 and y4. And the temperature has to be degree of freedom at the nodes, which is a primary variable. So we will have T1E, T2E, T3E, and T4E. So these are the temperature values. But now what we do, this element arbitrary quadrilateral in the physical coordinate space is mapped to natural coordinate space. So there is a mapping. So this is what this symbol I have shown here is for mapping. So this is mapped to a square in the natural coordinate space. So this is a square and the coordinates are xi and eta. The nodes are same. So node 1 here is mapped to node 1 here, node 2 is mapped to node 2 in the natural coordinate space, similarly 3 and 4. Now if you look at the coordinates, because the natural coordinates are varying from -1 to +1, so the coordinates of this node 1 would be -1 in the natural coordinate space. The coordinates of this would be 1 and -1. The coordinates of this would be 1 and 1, and the coordinates of this would be -1 and 1. So these are the coordinates. The temperature values are going to be same. So if we take corresponding point here, these coordinates would be xi and eta. So if the no, the same, this point P is corresponding to this point P in the physical coordinate space is corresponding to this point P in the natural coordinate space. So the temperature, if it is T here, at the corresponding point also the temperature would be T. So therefore, when you look at the degrees of freedom, it would be T1E here, T2E here, T3E here, and T4E here. So now in this case, you see the degrees of freedom, DOFs. So if I write DOFs, degrees of freedom, in this case temperature, T1, T2, T3, T4 are same in both the spaces, the physical coordinate space and the natural coordinate space. So now when we do the interpolation, so now since we have to relate also, no, we one is that we need to assume an approximate solution for temperature. So now rather than assuming the approximate solution of our temperature in terms of xy, we will assume the no approximate solution for temperature in terms of natural coordinates xi and eta. But we also have to, when you we assume the temperature in terms of natural coordinates xi and eta, but in the integral functional we need the derivative of temperature with respect to x and y. So therefore we also need the relationship between xy and xi eta. So we also need to assume the relationship between xy and xi eta coordinates also. So now that means the interpolation of temperature is going to be there, and also the interpolation of xy coordinates is also going to be there. So now when I talk of interpolation, and in the interpolation I am also going to introduce another concept called isoparametric formulation. So another terminology is coming, isoparametric formulation. So I will explain this when I know discuss the temperature approximation. So let us say T. Now when we say interpolation, we are assuming an approximate solution. But here we want to assume the approximate solution in terms of natural coordinates xi and eta. So it would be a0 plus a1 xi plus a2 eta plus a3 xi eta. The form is same like what we were doing because there are 4 degrees of freedom. So we need to assume an approximate solution which has got 4 constants. So we'll have constant term, linear term in xi eta, linear term in eta, and a bilinear term in xi and eta. So now let us say this is equation number. I think I earlier numbered some equations, so let me check that. Yeah, so let me call that as equation number 2. So let us say this is equation 2. But at the same time, we also have to relate x and y with xi and eta. So we write x is equal to, say now b0, but the same kind of a polynomial. b1 into xi plus b2 into eta plus b3 into xi eta. And similarly, y coordinate also is written in terms of xi and eta, natural coordinates. So c0 plus c1 xi plus c2 eta plus c3 into xi eta. because we are assuming the temperature in xi eta and we need the derivative of temperature in xy. So we need the relationship between a xy and xi eta, and that is why this is yeah, involved. And now if you have this kind of an approximation, so when you are having the assembly of any arbitrary quadrilateral in the physical coordinate space, so let us say that we have this arbitrary geometry and we discretize this using two elements. This is element 1 and this is element 2. These are the two common nodes. So when you look at this edge, when I talk of element 1, so this edge is mapped to kind of, you look at, although it's the same square element, but for the purpose of showing, let me show like this. So element 1 is actually mapped to this xi and eta, element in the xi and eta coordinate, and this is element 1 and this is element 2. So when we are moving along line AB, so we are basically moving along this line, and when you are moving along this line, you see xi is constant, that is along AB. For when you're talking of element 1 along line AB, xi equal to +1. When you are moving along no, in element 2, xi will be equal to -1, but they would be constant. So when you put that xi equal to constant, either +1 or -1, you will see that t is going to be linear function of eta, and at A and B we have the common values of temperature in both the elements, so we will get a unique variation of temperature along line AB. Although when we are moving in the natural coordinate space in the line AB, along line AB, we will be moving corresponding to this line AB in the physical coordinate space. So it would satisfy the compatibility condition both in the natural coordinate space and the physical coordinate space. So that is the advantage of this natural coordinate formulation. So basically, I can say that this interpolation satisfies the inter-element compatibility, as I explained. So this interpolation in natural coordinate space, this interpolation in natural coordinate space satisfies inter-element compatibility. And this is very important to get the no, if you use the element, if it is not compatible, it will not, one is that it will not give the monotonic convergence. Monotonic convergence means when you increase the uh, number of elements, so no, the element is it is like this. So if I, let's look at the temperature value at some location, t at some location, say t at some location, let us say x star and y star. X star and y star are the coordinates, and this side if we look at the number of elements. So when we plot this distribution, if the element is actually compatible, then you get this kind of a convergence curve. So we have a smaller number of elements, you get this as a temperature. Then you say double the number of elements, you get this as the temperature. Then you further increase the number of elements, you get this. Further increase the number of elements, you get this as the temperature. You see that this two the values, this will be some mesh 1, let us say, with lesser number of elements. This would be mesh 2, more number of elements. Mesh 3, still more number of elements. Mesh 4, highest number of elements. So you will find that these two, mesh 3 and mesh 4, are giving you the almost the same result. That means the solution has converged. So this kind of convergence behavior you get from the compatible element. So this is from a compatible element. If the element is incompatible, so then the no, this curve you may get something like this, and the convergence may finally get significantly delayed. So we mesh 1 may give you this result, mesh 2 may give you this, mesh 3 may give you this result, mesh 4 may give you this result. So this gives the oscillating convergence, so which is difficult to through that it is difficult to ensure the whether the solution has converged or not. That means whether we have got the accurate result or not. So this kind of convergence behavior you get from the incompatible element. Yeah, so now let us continue the formulation. So we have discussed the advantages of element formulated in natural coordinate space. So it can be arbitrary quadrilateral, but still it will satisfy the inter-element compatibility condition. I have used one more terminology here. So I just want to tell you that I said here isoparametric formulation. So what does mean actually in the natural coordinate space formulation, you will always interpolate the independent unknown variables. So in this case, a temperature are for plane stress, plane strain problems, displacements u and v, and the xy coordinates. And in case of 3D, say you will have temperature and xyz are displacements uvw along xyz directions and the coordinates xyz. So you would be interpolating both. If the interpolation of the unknown variables and the geometry, that is xy coordinates, is same, then it is known as isoparametric formulation. And if the interpolation of geometry is of higher degree polynomial compared to the unknown variable, then it is known as superparametric formulation. So and if the interpolation of geometry is lower than the variables, then it is known as subparametric formulation. So let me define what is isoparametric formulation. So this is specific to know this natural coordinate space formulation. So isoparametric formulation. So in this case, the interpolation of unknown variables. So in this case, we have t is same as the interpolation of geometry, that is xy coordinate in this case. So if we have this kind of and this is what is most commonly used, isoparametric formulation. So packages like abacus, census, nastran, these packages you when you use for designing doing the finite element analysis, you will find that all the elements you would use 2D and 3D elements would be isoparametric elements. But since the concept is there, I just want to give the definitions. So then you have super parametric formulation. Super parametric formulation. So super parametric formulation means interpolation interpolation of geometry. When I say geometry means in this case x and y coordinates. And when I say interpolation means the whatever expression we are assuming in terms of coordinates xi and eta. So interpolation of geometry, that is xy coordinates, is of higher degree polynomial compared to interpolation of dependent unknown variables. So this is known as superparametric formulation. So similarly, there is a subparametric formulation. So it is just the reverse of this. So when you say subparametric formulation, so in this the interpolation of geometry, that is x and y coordinates, is of lower degree polynomial compared to, so in this case it is higher as you see, and only changes here it is lower. So compared to interpolation of dependent unknown variables. Yeah. So if you don't follow anything, please stop and ask. So yeah, you can ask anytime, any question, whatever you have. So now, yeah. So this is what. Yes, yes, please.
So can you give examples of this?
Yeah, so the examples would be, say, for example, for the superparametric formulation, we interpolate temperature as, let us say, A0 plus A1 xi plus A2 eta plus A3 xi eta. But X and Y we interpolate as B0 plus B1 xi plus B2 eta plus B3 xi eta plus B4 xi square plus B5 eta square plus B6 xi square eta plus B7 xi eta square. So that kind of a thing. Similarly, in the subparametric T, you interpolate as, say, A0 plus A1 xi plus A2 eta plus A3 xi eta plus A4 xi square plus A5 eta square plus uh, A6 xi square eta plus A7 xi eta square for temperature. But X and Y you do B0 plus B1 xi plus B2 eta plus B3 xi eta. So, but usually, as I already said, what we use is the isoparametric formulation. So, the packages and all, whatever elements you are going to use, you will use, no, they are the library, element libraries of isoparametric elements. No, you rarely, of course, if you write your own code, for no code in MATLAB, Fortran, or C, you can use the other types of element. But in the packages, you have only isoparametric elements. And this subparametric and superparametric are used if the geometry is simple, but the variation of the dependent variable is quite complicated, then use basically subparametric formulation. And if the geometry is complex but the unknown variables are varying quite smoothly and linearly, let's say, then use the superparametric formulation. So let us continue then with the yes, please. Hello. Yes.
Nothing, nothing, sir.
Okay. So let us continue with the isoparametric formulation. So we continue with the isoparametric formulation. So next step is, as you know already, that no we express the unknown constants in terms of the values of the variable at node points. That is elemental degrees of freedom. So we have got this approximation, and now we need equations for finding out A0, A1, A2, A3 in terms of T1, T2, T3, and T4. And similarly, we have to express B0, B1, B2, B3 in terms of X1, X2, X3, X4, and C0, C1, C2, C3 in terms of Y1, Y2, Y3, Y4. So we write the corresponding equations. So now if we look at T1E is the value of temperature at node 1. And at node 1 you see, let me write again, in the natural coordinate space this is xi and this is eta. Hmm. So this is node 1, coordinates are -1 and -1. This is node 2, coordinates are 1 and -1. This is node 3, coordinates are 1 and 1. This is node 4, coordinates are -1 and 1. So at first node, both xi and eta are -1. So you will get, no, when you put that in the expression for temperature, which is A0 plus A1 xi plus A2 eta plus A3 xi eta. So you will get this as A0 minus A1 minus A2 plus A3. And then T2E will be equal to, now you put these coordinates. So where xi is +1, eta is -1. So A0 plus A1 minus A2 minus A3. That is what you will get. You are substituting no in this expression. T equal to a0 plus a1 xi plus a2 eta plus a3 xi eta. So you are putting the nodal coordinates. And then T3 is the value of temperature at node 3, where xi and eta both are plus 1 plus 1. So this will come out as a0 plus a1 plus a2 plus a3. And then you will have T4e for the coordinates xi eta are minus 1 and plus 1. So you will get a0 minus a1 plus a2 minus a3. And let us say this whole thing is equation 3. So I know first step is to solve equation 2 for a0 a1 and similar equations you would be able to write for x1 x2 x3 x4 and y1 y2 y3 y4 in terms of the corresponding constants b and b's and c's. So now if you what we can do is we can solve this equation 2, solve equation 2 for a0 a1 a2 a3 and substitute the solve equation 3, not 2. This is equation 3. Solve equation 3 for a0 a1 a2 a3 and substitute in equation 2. The equation 2 earlier I have numbered. So if what you will actually get ultimately and collect the coefficients of T1e, T2e, T3 and T4e. So you will get that as N1 into T1e plus N2 into T2e plus N3 into T3e, N3 into T3e plus N4 into T4e. So this is what you will actually get. And similarly, when you do the same thing for x and y coordinates, so similarly we'll get x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4, and also y will be n1 y1. So this, because in the isoparametric formulation the approximation of t x and y is the same, so you see the same shape functions n1 n2 n3 are appearing in t, in x and also in y. So we will have n1 y1 plus n2 y2 plus n3 y3 plus n4 into y4. So this is what you are going to get as the interpolation. Now I need to write basically the shape functions. So let me define these shape functions. So how I'm going to define the shape functions I will explain. So rather than finding out the solution of this equation and then putting back in equation 2, we can directly write the shape functions. So I'm going to tell you how to directly write the shape functions. So if you look at the shape are interpolation functions. So these are ni, that is n1, n2, n3 and 4. So again if you look at the element, this is a square in the natural coordinate space, xi and eta. This is node 1, this is node 2, this is node 3, this is node 4. And you would see the equation of this line is basically xi equal to 1. So you can write 1 minus xi equal to 0. The equation of this line is xi equal to minus 1. So you can say 1 plus xi equal to 0. Equation of this line would be eta equal to minus 1. So 1 plus eta equal to 0. Equation of this line eta equal to 1. So you can write 1 minus eta equal to 0. So now when you write n1, as I explained earlier, for the rectangular element formulated in local coordinate capital XY, so same logic we use here. So when I want to write the shape function for n1, so I take the lines covering nodes 2, 3 and 4. So one line is this 1 minus xi, and the another equation of this line is 1 minus eta. So we have 1 minus eta, but then you'll have to make sure that this is unity at node 1. So node 1, the coordinates are xi equal to minus 1, eta equal to minus 1. So if I put those values over here, I will get 4. So then I need to divide it by 4. So now if I have n1 as 1 by 4 1 minus xi into 1 minus eta, it would be unity at node 1 and 0 at node 2, 3 and 4. That's the property of these shape functions. Similarly, if you look at n2, so now if you look at n2, n2 is corresponding to this node. So you take the equation of this line and this line. So n2 would be 1 plus xi into 1 minus eta, and the coordinates of node 2 are xi equal to plus 1 and eta equal to minus 1. So these two will give you again 4. So I need to divide it by 4, so that n2 is unity at node 2 and 0 at node 3, 4 and 1. So same way you write the shape function n3.
Sir, why are we dividing it by 4?
Because we want to make sure that it is unity at the corresponding node. So n1 shape function is the shape function corresponding to node 1. So it should be unity at that node. So now if I node 1 means the coordinates are say minus 1 and minus 1. So if we put here, so 1 minus minus 1, you will get 2 into 1 minus minus 1 again 2. So 2 into 2, 4. In the numerator we are getting 4. So therefore I am dividing it by 4 so that I get it as unity at node 1. So same thing for no n2, n3, n4. Is it clear?
Yes, sir.
And the why we are doing that itself is because no, when we look at this interpolation, t equal to n1 t1 plus n2 t2 plus n3 t3 plus n4 t4. So when I evaluate t at node 1, so it should give me just simply t1e. So that means no, the n2 n3 n4 have to be 0 and n1 has to be unity, so that I get t1 equal to t1e. That equation is satisfied. So that is why we are doing that. And so similarly, if you look at n3, so n3 is this node. So we take the lines which are covering the other nodes. So this line 1 plus xi equal to 0 and this line 1 plus eta equal to 0. So 1 plus xi into 1 plus eta is the equation of these lines. And again at node 3, when I put xi plus 1 eta plus 1, it will give me 4. So I divide it by 4. And so similarly n4 is for this. So I take the equations of this line and this line. So 1 minus xi, and we have 1 plus eta, and then divide by 4. So these are the basically shape functions. So n1, n2, n3. The property of these shape functions is that n1 is unity at node 1, 0 at other nodes 2, 3 and 4. n2 is unity at node 2, 0 at node 1, 3 and 4. n3 is unity at node 3, 0 at 1, 2 and 4. n4 is unity at node 4 and 0 at 1, 2 and 3. So now if you look at the interpolation, you can write of course simply t, no sorry, this t as it is. So we are talking of temperature. So T can be written as in terms of these shape functions N1, N2, N3, N4 into T1E, T2E, T3E and T4E. And this can be written as basically no H into our standard notation H into D, where this is H and this is D. So this is equal to T. Now when we want to look at del T by del X and del T by del Y, so we need the derivatives of temperature with respect to x and y. But you see the temperature is written in terms of n1, n2, n3, n4. And n1, n2, n3 are explicit functions of xi and eta. So we can easily get the derivative of no t with respect to xi and eta. But we want to get the derivatives with respect to x and y. So how do we do that? So then we need to relate the derivatives no in terms of x, y and xi and eta. So before I write the B matrix, the temperature gradient in terms of B and D, let me talk of this concept how to get the relationship between the derivatives with respect to physical coordinates and the natural coordinate space. So let me write that derivatives with respect to physical physical space coordinates, that is x and y. So for that, to demonstrate this, let me consider a function which is a function of xy. So let us say that function is f of xy. And we know that in the natural isoparametric formulation, x and y are expressed in terms of xi and eta. So if I want to get the derivatives of f with respect to xi and eta, I can use chain rule of differentiation. So using chain rule of partial differentiation, what we can write is I can write del f, no, derivative of function f with respect to xi. F is explicit function of x and y, so I can differentiate it with respect to x, but then x is a function of xi, so I will have del x by del xi. F is also function of y and y is a function of xi, so del f by del y into del y by del xi. Why we are writing in this manner? Because x and y also we have expressed in terms of xi and eta. So we can easily get this and this because we have x and y in terms of xi and eta. So we can differentiate those expressions and get del x by del xi and del y by del xi. So we can easily get this. So similarly, if you look at del f by del eta, so del f by del eta would be now del f by del x because f is explicit function of x. So del f by del x into del x by del eta, and then f is also function of y and y is a function of eta, so del f by del y into del y by del eta. So now we take out the no function f out and just write the operator relationship. So if I write the operator relationship, that is just want to write the no, I want to take out the function f and only write the relationship between the derivative operators with respect to xi and eta. So I can write, no, here I am taking out f, so I will write del by del xi, and I let me also write this in the matrix form, and so the second is del by del eta. So these two of derivative operators can be written on the other side. So f is actually with these, no, del f by del x, del f by del y, del f by del x, del f by del y. So that I am going to f we are taking out. So inside we are going to have, no, these terms, del x by del xi, del y by del xi. So I will have here del x by del xi and del y by del xi, and this side we will have the derivative with respect to x and y. So del by del x and del by del y. So essentially you are say getting here del by del xi equal to del x by del xi into del by del x operator del by del x plus del y by del xi into operator del by del y. So if you operate on f, you will get del f by del xi equal to del x upon del xi into del f by del x plus del y by del xi into del f by del y. So what is written over here? So we will get the same thing. Similarly, del by del eta can be written as del x by del eta, del y by del eta, and then this del by del x, del by del y, they are already there. So now in this, no, this is known as the operator relationship, derivative operator relationship, and in this particular matrix is known as J. That is the Jacobian matrix. We call it as Jacobian. So today, I am introducing many concepts, so you have to be a bit attentive. So this is no, it is referred to as Jacobian matrix. No, this is a 2 by 2 matrix for 2D problems, and for 3-dimensional problems it would be a 3 by 3 matrix, because then you will have three natural coordinates xi, eta, and zeta, and you will have three physical coordinates x, y, and z. So there this Jacobian matrix will become 3 by 3 matrix. So now if I write the so actually now what we are able to do, we are able to write now in this the derivative with respect to xi and eta in terms of derivative with respect to x and y, but we want just reverse of this. Why reverse of this? Because our shape functions are in terms of xi and eta, so we can easily get their derivative with respect to xi and eta, but then we want their derivative with respect to x and y. So then we need to express the derivative operator del by del x and del by del y in terms of xi and eta. So we need to take an inverse relationship. So if we write the inverse relation, So if you write inverse relationship over here, so you can say that del by del x, del by del y will be actually equal to inverse of this matrix. So that means we will have del x by del xi, del y by del xi, del x by del eta, del y by del eta inverse into del by del xi and del by del eta. So this can be no, this is J inverse actually, as you see over here. So you can call it as essentially this is nothing but J inverse. So you can also say that del by del x, del by del y is equal to J inverse into del by del xi and del by del eta. And now no, we of course have to find the inverse of J matrix. So let me say that J inverse. So you get the first 2 by 2 matrix, this Jacobian matrix. Find out its inverse, and the inverse is also going to be a 2 by 2 matrix. So let us say the elements of the 2 by 2 matrix are J11 star. These are the after finding out the inverse, J12 star, J21 star, and J22 star. So this is, let us say, J inverse. So then from this relationship you can easily say that del by del x will be equal to J11 star into del by del xi plus J12 star into del by del eta, and del by del y. So just please note a difference between x and eta. So this is x over here. So this is x and this is eta. So del by del y would be then the second row. Second row would be J21 star into del by del xi plus J22 star into del by del eta. So our ultimate aim was to write the derivatives of the shape functions with respect to x and y. So now if I write no the ith shape function, so I can say del ni by del x. So now I write ni here. This is the operator. I operate it onto ni. So I will get del ni by del x is equal to J11 star into del ni by del xi plus J12 star into del ni by del eta. And here I is taking the values because there are four shape functions. So we'll take values 1, 2, 3, 4. Similarly, del ni by del y will be equal to, that is from this relationship. So we will get J21 star into del ni by del xi plus J22 star into del ni by del eta. So like this you can get the derivatives of all the shape functions with respect to x and y. Of course, we need to know the derivatives with respect to xi and eta, and that we can do easily. So if you look at the expression for n1, we have got the n1, n2, n3, and 4 I have written over here. So now here you have got these expressions for n1, n2, n3, and n4. So you can easily find out their partial derivatives with respect to xi and eta, and then substitute that in this expression and get the derivatives of these shape functions with respect to x and y. So you would be able to see that now del n1 by del xi, which is needed no in these equations, this equation and this equation. So this would be when you differentiate, because it is 1 by 4, 1 minus xi into 1 minus eta. So the derivative with respect to xi would be 1 minus 1 by 4
Excuse me,
into
sir.
1. Yeah.
Sir, can you just repeat from last 2 3 pages? Now I'm not able to understand what you are telling after so many differentiation. Just a
Okay.
brief, whatever you have written, sir. I'm not able to
Yeah, so
understand.
I will start from here. So see what I
Yes, sir.
have said. I have said let us consider any function f which is a function of explicit function of x and y. Explicit means it is expressed in terms of x and y. And of course x and y in the isoparametric formulations are also functions of xi and eta. So then I said we want to, let's find out the derivative of f with respect to xi. So since f is a explicit function of x and y, we can differentiate it with respect to x and y. So I differentiate it with respect to x, so I write del f by del x. But then ultimately we want the derivative with respect to xi. So then we need to differentiate this x with respect to xi. So this is del f by del x into del x by del xi. But f is also function of y, and since y is a function of xi, so that will also contribute in the del f by del xi. So then plus we have del f by del y into del y by del xi. So you will get these two terms in the del f by del xi, where f is explicit function of x and y. So similarly, I have written del f by del eta. So since f is a function of explicit function of x, so you will see that this is x, no? So that you have to keep, this is x. So we have del f by del x, and then x is function of eta, so del x by del eta gives the contribution to derivative with respect to eta, and because f is also function of y and y is a function of eta, so that will also contribute in the derivative with respect to eta. So we write del f by del y into del y by del eta. So this is how I have written these two equations, and these equations are the basis for what we have discussed subsequently. So are you clear about these two equations? Then I proceed further. Hello? Do you understand now how these derivatives are written
Yes,
or
sir.
no?
Yes, sir.
Because f is a function of xy, and xy is a x and y are functions of xi and eta. So when we want the derivative with respect to xi, we differentiate f with respect to x, x with respect to xi, and plus f with respect to y, y with respect to xi. That becomes the total derivative with respect to xi. And same thing is written for eta. Then what I have done here, in this I have just taken out f actually and only written the operator relationship. So this side I have no, if I take out f, I am left with del by del xi and del by del eta. So that is what I have written here. And this side when I take out f, I get del by del x and del by del y. So del by del x and del by del y I have written over here. And then this del x by del xi, del y by del xi, del x by del eta, and del y by del eta I have written as this matrix. So if you look at, no, if you would have kept f also, so you would have got del f by del xi, del f by del eta equal to this 2 by 2 matrix into del f by del x into del f by del y. And if you multiply these two right side matrix and vector, you will get exactly this equation. So that is what I have done. And then I said refer this is referred to as Jacobian matrix. This del x by del xi, del y by del xi, del x by del eta, and del y by del eta is a Jacobian matrix. This is actually the kind of a transformation between coordinates xy and xi eta. So this is the transformation Jacobian matrix. So we call it as a Jacobian matrix. Now what I said is, because the shape functions, ultimately we want the derivatives of the shape functions with respect to x and y. So but they are expressed in terms of xi and eta, so we can easily get derivatives with respect to xi and eta. So we need the inverse relationship. So if you just take, if you pre-multiply by inverse of this matrix, you can express del by del x and del by del y in terms of del by del xi and del by del eta. So that is what I have written here, that del by del x and del by del y is j inverse into del by del xi, del by del eta. So now the same inverse of this is written over here. And then in the notation form you can say del by del x, del by del y equal to j inverse into del by del xi, del by del eta. And then I said j is of course defined by this. Now you have x as a function of xi and eta, y as a function of xi eta. So you can get these basically no, this 2 by 2 matrix. Then you can find out its inverse. And I said let's its inverse is given by this. And then I have said no, then no, if j inverse is this, so if you take the first row right hand side, if you multiply the first row with this, so you will get j11 star into del by del xi plus j12 star into del by del eta. So that is what I have written here. And similarly, no, this, if you take the second row over here, so that means this row multiplied with this column, so you get j21 star into del by del xi plus j22 star into del by del eta. And now you can operate these operator on any function. So our specific interest is to get the derivatives of shape functions with respect to xi. So if I operate this del by del x on ni, so I get del ni by del x is equal to j11 star into here ni comes, so del ni by del zeta del high plus j12 star del ni by del eta. And this is for I going from 1, 2, 3, 4. So you can do this for n1, n2, n3, and n4. And same thing for the del ni by del y. So same way, this relationship is written. So is that clear now?
Yes, sir.
Okay. So then I think then I was just telling you that the you can easily get the derivatives of the shape functions with respect to xi and eta. So I have already know, I just said n1 is 1 by 4, 1 minus xi, 1 minus eta. So its derivative with respect to xi would be this, and similarly derivative of n1 with respect to eta would be minus 1 upon 4, 1 minus xi. And same way, you can get the derivatives of the other shape functions. So for example, del n2 by del xi, you already have the expression for n2. So that would be del n2 by del xi would be 1 by 4, 1 minus eta, and del n2 by del eta would be equal to minus 1 by 4 into 1 plus xi. And like that you can do for the n3 and n4. So I think I want to stop here, and if you have further questions and doubts, now you can ask. We will continue in the next class. So yeah, you want to ask any other question, any doubt? So yeah, what we are trying to discuss is the basics involved with the finite elements, and of course wherever possible I am giving some examples which are kind of representative application examples. And of course more complex real life problems have to be either solved using a developing a code in MATLAB, Fortran, C, or using the packages like ANSYS, Abacus, Nastran, NISA. So obviously those complicated problems cannot be done over here. So that is how, this is, and this understanding of this finite element formulation will help you using this softwares judiciously. So when you actually work on design problems, you will understand that how you are able to choose, select the elements, what the quantities you are calculating, and how you are able to do. So that is what can be done actually. That's what we can do. So yes, any other question, any doubt? Okay, so then I stop. Thank you all for your attention.